All right. So
Okay,
recording.
okay, everybody. I'd like to welcome you to tonight's Seattle Quantum Computing Meetup. Today we have a speaker, Sam Burdick, and he's an open source quantum developer. He's going to present to us on quantum error correction, and he's open to receiving questions during his talk. You can stop and interrupt him or put them in the chat. And with that,
Yep.
I'm very appreciative that Sam's with us tonight. I'm very much looking forward to learning more about quantum error correction, and I'll hand it over to him, and he can let us know how he got involved or interested in this topic and all the rest of it. Yeah.
Oh, okay. Yeah, I could actually start with that. I didn't prepare a slide for that, but so thank you, Natalie, for that introduction. I am actually pretty new to quantum computing. I decided to start contributing to open source quantum computing a few months ago, and I messaged some of the maintainers at SQCM asking if there were any open source projects that really needed attention. And Victoria Molly, who's one of the maintainers at SQCM, referred me to the Topological Quantum Error Correction group that is developing a circuit editor for essentially, they're called stabilizer codes, and we'll actually talk more about what those are exactly within this talk. And that group is being led by Dr. Austin Fowler. He's a research scientist at Google Quantum AI, and he's part of the team that's developing their quantum computers. And I guess now I can kind of segue into the talk. This is quantum error correction, and particularly, quantum error correction is really important. So I'm going to go ahead and start. The motivation here to perform quantum error correction is that qubits have unacceptably high error rates on their own. They're very easily disturbed by external noise because you're working on the scale of photons and electrons, and any small forces around the qubits can disturb their state and produce undesired results. And so in order to mitigate these errors, we have to perform error correction. And this is actually essential to doing quantum computation. And so this is an image from Google's research blog. Currently, at Austin's lab, they have a 100 qubit prototype. And this is a superconducting, super cool superconducting quantum computer. And essentially, the error rates are around 1 in 100 before error correction. And that's still obviously unacceptable before we're actually able to scale this. And so I believe this 54 is their Google Sycamore that produced quantum supremacy, the quantum supremacy claim that Google made back in 2019. And so we're kind of at this 10 to the second area. And in a couple of years, we'll hopefully increase up by a factor of 10, and then by another, and so on. And we're still not even at the point where we have a long-lived logical qubit. Like, imagine your hard drive not even having a long-lived bit. Like, we're not even there yet for quantum computers. So there's a lot of engineering and actually even a lot of basic science that's still being performed in order to make scalable quantum computers possible. I heard a noise. Anyway, so at this point, and so yeah, by the way, just reiterate what Natalie said. If you have a question, feel free to post it in the chat or actually just interrupt me. And everyone's free to do that because this isn't a super long talk, and my goal is to help produce greater understanding of the topic. So This is the kind of the state of the affairs for qubit error rates, and obviously this is not really where we are not where we want to be right now, but there's hope within the community that 2024 or 2025 will be the times when we really have a good, with the scientific community really has a good understanding of how to scale quantum computers. And really the important thing is getting this building these quantum error correction circuits. So what is a quantum error correcting circuit, you may ask? So here's an example of the repetition code using 3 qubits. If you're unfamiliar with this notation, this is a control NOT gate here. It's analogous to an exclusive OR gate in classical computing, but again, we're manipulating a quantum state where instead of zeros and ones, we have a superposition. Instead of zeros and ones, like exactly at all times, we have a superposition of 0 and 1. So suppose we have a state phi that's just a kind of a normal qubit, the way you normally define it. And suppose, for the sake of argument, in the next slide, this seems a little bit of contradiction, but this is just a basic textbook example. Suppose you take phi and we're able to perfectly encode it as the same state, but instead of one qubit, it's now 3 qubits. And the superposition of each of those qubits is the same as phi. And that's as psi, and we call this new one phi. And so let's start by passing each qubit of phi through this circuit. So we say let psi be this qubit, and that this qubit where we have 0, 1. And in the absence of errors, the output state, which is after the XOR gates have been performed, the entire system should be phi. Like, essentially, we get back to phi every time we run a qubit that's really equal to psi through it. And this is an example of the repetition code where basically we're copying a state over and running it through the circuit a few times. And this will allow us to detect any errors that have occurred, because if an error did occur at any point in the circuit's execution, then the output state will not be phi. So phi is sort of like a checksum, like a sanity check in a when you download a file from a website you may or may not trust. So any questions about the repetition code? Okay. So quantum error correction has some constraints that we have to overcome. The first is that arbitrary qubits cannot be cloned, and this was due to what's called the no cloning theorem in quantum mechanics. It was proven, I believe, in the 70s or 80s, and it essentially says that you cannot take a quantum state and make a copy of it because of all the hidden information in that quantum state. The other issue, and this is especially in contrast to classical error, is that quantum errors are continuous because the quantum states, the qubit states, are continuous. And when you have a quantum error that occurs, it again is a continuous transformation of the continuous state, and that is another challenge, because especially compared to classical computing, where every error is just a bit flip. It's not continuous, really. There are continuous effects that may have caused it, but in the quantum space, we have this third problem too, that measurement destroys the quantum information. We can have a state, we can apply gates, operators, errors can occur, but measuring it will only give you a 0 or 1, assuming we measure it in the Z basis. So luckily, all of these problems have solutions that we know. So we can't clone a physical qubit, but we can use many physical qubits to represent a single logical one. That goes back to this slide, where essentially we have a prototype for logical qubit that's 100 qubits, right? So we're not cloning anything, but we're replicating hardware to achieve logical continuity that we want. So I mentioned that quantum errors are continuous, and that is technically true, but really it's big. The nice thing is that every quantum error can be represented as a linear combination of what are called these Pauli errors. So Pauli was a famous quantum physicist from the 1920s, and these two kinds of these are the only two errors that can occur. Essentially, you can think about it that way: are X errors and Z errors, and they both have nice little 2x2 matrix representations. And I'll explain those in the next slides. And so this is a really significant. This is the first really key property of quantum errors that we understand, and that we can actually exploit if we want to build scalable error correcting hardware.
Hey, Sam.
Yeah.
This is Natalie. I have a question. So I was reading that we can have two kinds of errors in quantum. One is a bit flip and one is a phase flip. So I'm thinking that's
Yes.
probably the first one's the X and the
Yep.
second one is the Z. Does that
That's
sound
correct.
right? Okay.
That's exactly what it means.
It kind of makes it well, it's just kind of nice to have some other words, I think, to it, as
yeah.
in addition to Poly X, that sort of thing.
Yeah, it's as you say, it's a bit flip, phase flip. The terminology is consistent. My only caveat, and it is true, and you do have this. I think the mixture of terminology arises from the fact that we have sort of this both a continuous way of thinking about information in terms of complex numbers, as well as a more linear or more discrete way of thinking about information in terms of zeros and ones, like we're used to with computation. So, yeah. But you're right. X and Z is flip, phase flip. Yeah, sure.
Do the X and Z correspond to the axes on the Bloch sphere?
They so I'm not. I haven't really. I'm not as familiar with the Bloch sphere formalism. I know it represents a single qubit. Mm-hmm. It does. The answer is yes. There is a relationship between those, and that is where the terminology comes from. But it's a little more nuanced than that, I think, because the Z basis. So we usually write qubits in terms of the Z basis here, like 1 over 0 is 0 over 1, and the rules that I'm describing are actually in terms of the Z basis. But there's also, if you look at the Bloch sphere, actually there's a picture that explains it really well. This is what you're talking about, right? So
yes,
the Z axis here is the 0 state, where it's one of the two orthogonal Z basis states of a qubit, and then in the X basis, this is the plus state. And then the Y basis, we don't actually need to worry about that, because a Y is just X and Z at the same time. And so you're correct. There is a correspondence here, and it's somewhat nuanced.
Actually, I think that the definition of Pauli X gate is a rotation by pi around X, and Pauli Y is rotation by pi around Y. So basically, the XYZ in the Pauli gates are the axis that rotation happens around.
Right. That's a good point. They do correspond to rotation, and the Bloch sphere does illustrate that. I sort of omitted that specifically from the talk because it's at a lower level actually than what our work as in quantum error correction. But yeah, these are yeah. For those who are not unaware, though, I do want to get to the next kind of introducing this, so we're all kind of up to speed now. So the other thing is measurement destroys quantum information, but we can use measurement gates sort of judiciously to detect errors in a quantum circuit. I'll give examples of this later. We don't actually have to measure the state. We can use essentially ancilla qubits that are modified by the state in a manner similar to the repetition code, actually, and check those results. Someone wants to join. But then, ignoring some people. Okay. All right. Anyway, so Natalie asked, or do X errors correspond to bit flips? That's absolutely true. This is the matrix notation is that we have these is just it's basically like the identity, but we take the transpose of it. And if you want, you can just take X and multiply it by the 0 qubit to get 1, and that's this shorthand here. And we can take X multiplied by 1 to get 0. So it's a bit flip, and this is really only acting on the Z basis vectors or states. But these you can, if you have any qubit where you'd have alpha over beta in terms of the Z basis, it works the same way. It just swaps the number. It just swaps the term again for the alphas and betas. The superposition terms, the coefficients, I guess, is the mathematical term. And so those are bit flips. And then we also have phase flips. So phase flips are this Z matrix here. It's also kind of like the identity matrix, but we have -1 in the bottom right corner. And the Z error or Z matrix doesn't do anything to the 0 state. And on the 1 state, it changes it to -1. So pretty, and what's really nice is X and Z, these are every quantum error possible is in terms of X and Z. And that is one of the really important properties, again, that enables us to do the work that we're about to do. Well, I'll show in a moment here. So those are bit flips and phase flips. The primary mechanism for detecting Pauli errors are stabilizers or stabilizer circuits. So if you have if you have a circuit, you can have an X error at any point. In here, it's happening right here. And we have this input state that kind of looks like the Bell state, and it's serving as the controls to these stabilizers here. And I mentioned ancilla qubits a minute ago. That's this 0 qubit here. And again, it's actually being assuming there are no errors. This measured gate will return 0. But if an X error would occur here, then we would get a 1 in this measured qubit. And you may ask, well, what if you get 2 X's? Well, the problem is the problem with that is that X times X is the identity, and so this would actually produce 0 if there was an X error here. So there are limitations to this. But if we only have, let's say we build the hardware smart enough that we don't have that as often. We only have these more isolated errors. Then what the quantum computer produces is a stream of these detection events. That's the 0s, the 1s, the 1s. And when we have that stream of detection events, we can feed that into a classical computer, which can then determine where the qubits that are producing incorrect measurements actually are. Because again, all this is very probabilistic. These 1s and 0s can be due to one error, they can be due to multiple errors. And so the more information we have, the better job we can do of analyzing it. So that's it's called the Z stabilizer, and it detects an X error. And the reason for this somewhat confusing notation is just coming later. But yeah, this is a Z stabilizer circuit, and you can actually, all the circuits that I've shown, they work the way that I described, and you can actually verify that for yourself algebraically. It's a good exercise if you're trying to get into this stuff. But I won't. If anyone would like to see some examples of that, I could pull up a whiteboard and do that. Pull up a Jamboard. I could draw on it. We're doing perfectly well on time. So, and if not, we can. So that's how we detect X errors. And so for Z errors, we use X stabilizers, and so they work similarly, except now instead of the state that we're trying to work with as an algorithm, that state is now being modified by this this stabilizer. And so you might think, well, why would we want to do that? Well, if you'll notice that we're putting in superposition with the Hadamard gate some of the time, and then we have another Hadamard gate here. And so having an even number of Hadamard gates cancels each other out. Again, these quantum gates usually have the property where if you apply them twice, they're invert. So that's another property we can exploit when we're putting these things together. And so if we get a Z error here, this detector and this detector will return 1 for these measure qubits. And again, these measurements don't actually change the quantum state. And that's actually the fundamental property of a stabilizer, is it does not change the quantum state that we're working with. So actually, shit, I deleted a slide by accident. Oh my god. Okay, so that's fine. X and Z stabilizers are sort of the building blocks of what we call the surface code. And so the standard surface code looks like this. It comprises alternating X and Z stabilizers, which are represented by the white and gray tiles. Okay, so this is now a very abstract representation of a large quantum circuit. The square tile contains 1 measure qubit. You can think of it as being in like the center, and each corner here is a data qubit. And like I mentioned before, they produce a stream of measurements that indicate qubit errors. And one of the nice properties of these stabilizer circuits is that X and Z, the matrices, they anti-commute. So you have an X and a Z here. This is really just equal to Z times X. And that sort of symmetry allows us to build these 2-dimensional grids that actually can preserve quantum information and perform computations in an error tolerant way, which was our goal. This is the surface code. It's getting more into like the abstract, and this is actually what we're trying to build. We're building a service that allows you to create these in the browser and do some performance analysis. That's what my group is working on currently. And the surface code is the object of study in what we call topological quantum error correction. And so surface codes allow correction of errors that form what are called topologically trivial rings and chains. And so if you have like a group of errors that occur like in like say 2 of these corners, this will be detected. Someone wants to join, welcome in. And what this topologically trivial also really mean? It's that they're confined to specific components, but they don't affect the overall system. They we're not talking about broader like systemic errors that would affect the entire circuit. That would overwhelm the whole quantum circuit, and we wouldn't be able to do anything with that. But if they occur in localized points, like the in the examples I gave, those are the kinds of errors that we're able to correct. And so there's a really great paper from Austin Fowler, who I mentioned, and Craig Igney. He's a colleague of his. They've done a lot of work on implementing this stuff in software as well as hardware. This is a diagram that describes how to perform an XX measurement. So that's an X measurement of 2 qubits. And it's done by splicing together these 2 surface codes. And we'll actually perform many measurements across these qubits. That's these blue dots. It's kind of hard to see. And then splitting it apart again gives us the measurement results. And so this whole splitting and merging basis is why we call it, is another reason why we call it topological quantum error correction. If you've ever had topology, you know, like the meme is like, you have a coffee mug and that's topologically equivalent to a donut. We don't really care about like the exact shapes per se, but we care about the relative placement of things as well as being able to localize things to like a specific object. And essentially, if the way Google is building quantum computers is to have large surface codes, have many surface codes, and that translates to a large scale quantum computer. And so that's actually all the content I had prepared for the day. I don't have any. I don't have any code examples because I didn't feel like I just felt like I want to have a more conceptual introduction. If you're interested in coding this stuff, though, I would invite you to look at our GitHub repository. If you just type in, I'll just go to GitHub right now. I'll show this tab. So this is TQEC. We have a pretty good sized group right now. We meet once a week, and we're should put a link in the chat. And yeah, there you go. And I'll share the slide deck here as well. Looks like we're having some articles about quantum error correction. Yeah, suppressing quantum errors by scale as surface qubit. I don't know who is involved with this paper other than it's just anonymously by Google. So this is a very exciting and trendy area right now in quantum computing. And I think really the best way if you're trying to get started is to to participate in this space. We have a lot of open issues. There's a lot of engineering problems that really need to be solved. So if you're still kind of getting comfortable with quantum computing, we're happy to teach you. Austin is great. He's really great. He's really great at explaining this stuff, and we've all sort of been working together to facilitate this project. And so we have both a back end that's written in Python. That's an abstraction layer to STEM and Circu, and those are the quantum computing libraries. And the front end, which is most of what I've been working on, is written in React, and it's essentially a circuit editor. I can actually pull that up right now. We have a live version. I believe I pushed this up today. So here's the live version. I'll put this in the chat. So and this can actually represent any theoretically any topology for a two-dimensional quantum computer that has this grid layout. I believe IBM has like a honeycomb layout that uses hexes. And so what you can do is you specify what's called a qubit constellation. Essentially, you put down some qubits, and you say, okay, these are like this is like the basis of the unit cell, and then I specify a tiling that kind of tells it how it'll duplicate all these qubits into the viewport. So I found as a unit cell, and now I have essentially all of these qubits to work with. And I can say create a plaquette, and so plaquettes are really just the tiles that I mentioned in the surface code. And so I can define the template first, basically by selecting a subset of the qubits, confirm template, and then I select some qubits here. Plaquette, and then let's go to the triangular plaquette, and I can change its color to either like purple or yellow. I think I should be able to make a score plaquette as well. Yep. Let's delete that. Oh, good, it didn't crash. Yeah. We don't have an actual like circuit editor yet. This is just like putting down qubits and plaquettes, and a plaquette could be any shape you want. And this would be like have, you know, these corners form the measure qubits, and then there's a data qubit associated with it. And the purpose of these red qubits would be like, say, this is like a template that I can scale, and then later on you'll be able to scale it up. We have a lot of tasks going on right now. We're only really just getting started at this. And if you have any front end, if you're interested in this stuff and you're comfortable with JavaScript, or even you just want to do it, then I encourage you to participate. And really, that means even if you can't make the meetings in over, it's like 8:30 a.m. on a Wednesday, which is not really doable for everyone. So, and because all that stuff gets recorded, we do spend a lot of time talking about quantum computing and quantum error correction, akin to the way I've been, and that's mostly facilitated by Austin, who's an expert in this stuff. So, I think that's really all the content I have. So, I'm going to leave the floor open for any questions.
Yeah. Okay. Hey, thanks so much, Sam. That was great.
Mm-hmm.
So I found these. I put a couple of links in the chat. For one was just an article in Physics World that's titled "Breakthrough in Quantum Error Correction Could Lead to Large-Scale Quantum Computers," and it's talks about the paper that the Google Quantum AI team released, which in February of last year in Nature, suppressing quantum errors by scaling a surface code logical qubit. So I don't know. From what I can tell, I mean, it's a breakthrough. I mean, I don't know. It seemed like people were pretty excited about it.
It is. For me personally, like, the challenge has been to really be able to understand this stuff from the perspective of a computer scientist, because I don't have any background in like physics or quantum mechanics or anything like that. I'm coming in really purely as like a computer scientist, software developer background. And what I found is that if you're interested, there are some like homework exercises for you to do. We actually have we have a lot of resources, and in our drive you can work with on your own. You can email, chat for help. There's a lot of people who are really curious and are really eager to share, and that's it's a really fantastic community to be a part of, I think. Yeah, I'm looking at this paper now, like looking at this like diagram. The implementation is kind of, we're building something very similar looking to that. Like figure 1A is building essentially that, but in the browser. So you'll notice actually in Figure 1A in the Nature paper that Natalie posted, the x-axis shows x sub L, which is x logical, and then you have z sub L, which is z logical. Sorry. That's basically to show that you know, I don't actually know what that means exactly. I'll have to read the paper to really understand it better. But yeah.
Logical
Anyway, thank you,
operator.
Natalie.
Logical. It says, let's see, logical operator ZL. Oh, logical
Yeah.
operator ZL and logical operators. I see. So, I guess every dot in Figure 1A is a qubit. Looks like. Would you agree with that? Is that?
Yes.
And then
Each dot. Yeah. So each square, there's 4. Each corner is a measure qubit, and the center is a they're data qubits. The center one's a measure qubit.
yeah, the blue ones, yellow is data qubit.
Blue is red.
And then blues measure qubit.
Mhm.
Yeah.
So is participation in this project how you learn most of what you know about quantum error correction?
Well, I would say for me personally, participating in the group overall, most of the project work that I've been doing, specifically in the code, has actually not been really involved with any quantum libraries. Which it's writing a UI that manipulates geometric shapes. And a lot of my own learning actually in quantum error correction has been more kind of traditional book style learning, where it's like doing exercises, solving circuits. So I've been doing that on top of the development work that I have going on. And yeah, it's kind of a multi-pronged approach where when I say participating in the group, we have a forum too. You can ask questions. People are very quick to answer. So it's really it's a multifaceted approach, really. For me personally, to learning this stuff, because I don't have a background in quantum computing really beyond what I've done within the context of this project.
One thing I was reading in the Physics World article is that someone commented that the surface code is the best practical method for scaling, and I guess he was saying in 2D.
Right.
Is that how? Can we do error correction in 3D?
Yes, we can.
Yeah. Okay.
We can.
And would we
can
not be
do
using?
more?
Would we still be using a surface code, or would it not be a surface? Would it be more like a volume code, or no? I don't know. The surface reflecting the 2D, or I wonder.
So it is actually. There is kind of an implicit third dimension here. If you look at Figure 1 in the Nature paper again, if you look at 1B, you have two physical dimensions that the qubits are laid out on. So it is a 2D surface code, but you also have the time dimension because you're running the circuit over and over and over again and basically getting a best guess from those results.
Yeah.
It takes about 1 microsecond to run the entire thing. And that's 100 qubits. So, you know, there's still a lot of work to be done in terms of
that would be slow, I guess, is kind of what we would say.
We're used to classical computing. Things happen on the order of 3 orders of magnitude faster.
Yeah. So I think that it seems like I think for cramming qubits together on some hardware, there's talk about doing, physically aligning them like in a 3D shape.
Yeah.
Like,
I believe
yeah.
To answer your question, I believe the surface code formalism can be extended to 3D. Yes, actually, I know for a fact that it can.
Yeah, it just
I know it's done through at least with the time dimension, but I'm not aware of any implementations where there's 3 space dimensions as well as a 4th time dimension. I assume that's a thing you can do though. But again, that would be, you don't have NQ. I believe still the surface code. It could basically be considered like a stack of surface codes at that point. But I haven't seen that. I don't believe that's what they have at Google.
yeah, right. Yeah, I think like Michelle Simmons down in Australia, and they're doing a different kind. I think not superconducting qubits. Like IBM's got that same kind as Google with a flat planar layout. So I guess in the Physics World article, it was mentioned that what we need is 1 in 1 million error rates, as opposed to say 1 in 100, like you mentioned, or 1 in 1,000, wherever the chips might be now, just to also kind of give a sense of where we are. And then also it sounded like the author was saying that another type of error that could happen is caused by cosmic rays, and the surface code wouldn't protect. We would protect against or detect, be able to correct for that.
Right. My understanding is that cosmic rays that is one of the things that they've done a pretty good job of protecting against the hardware level.
Yeah.
But obviously the X and Z errors are unavoidable. It's how strong mechanics is. So.
Okay.
Oh, Ross, did you have a question?
I just unmuted myself.
Yeah.
I have a couple of questions. So Sam, in the surface code that you are looking at, what's the relationship between the number of logical qubits and physical qubits? Is it a square?
Yes, it's about. Oh, you're asking like asymptotically. Right now, well, that's actually it's actually hard to say that right now, because if you look back at the slide, again, go back to presenting again. The slide that had the I think this is like the first slide I had. Yeah, this one. So right now we have 100 qubits, physical qubits to 1 logical qubit. Technically, the surface code that I showed here, this could technically produce 1 logical qubit in theory. But we're not able to it's not the hardware isn't good enough that this structure can actually produce a logical qubit. And we're at the point where the goal is by next year to have a long-lived logical qubit that comprises 1,000 physical qubits. And so the hope is in the coming decades that these numbers will eventually go down, and but we just don't have that. The technology just doesn't exist yet.
Okay. Yeah. So, I think that, I read somewhere, but I cannot. Well, he did not read any details. That late last year, IBM was showing some system where the dependency was almost linear. Like for every logical qubit, they were requiring 12 or 13, I don't remember, physical qubits. And as they were scaling up the number of logical qubits, the number of physical qubits was growing linearly, almost slightly faster than linear.
Did they?
I don't have more details, so I need to. I know that it was in December, so reference point.
Actually, there was a really exciting paper that came out from Harvard that I believe that was actually done in conjunction with IBM. They used a different approach than what's being done to Google. I haven't actually read that paper, but that when I had asked Austin a similar question, and he pointed me to he cited a paper from from last December. I think we might be thinking of the same thing, actually.
Mhm.
It came out, it was from Harvard.
Mhm.
But there were a lot of IBM folks in the author list. And so
Mhm.
they actually, no, I'm just curious. I'm going to look this up. Harvard. I'm just going to dig through my email to find this. Or actually, no, I don't have to do that. I have it downloaded somewhere.
12 to 13 sounds like a pretty low. I mean, it's that's a number that's come down a lot. It
Mhm.
sounds like. Oh, that's neat.
Yeah.
Do you think it was related to the QEra group who's at Harvard, but you know, IBM's hardware and QEra is hardware, so I don't know if those two, if that would make sense. Maybe not. Was it IBM as in they're talking about their own hardware? Do you know, Ross? Yeah.
I don't want to deceive you in any way because I think it was IBM's hardware, but I'm not sure. So
Yeah.
I need to find it.
So I post a link to a paper.
Mhm.
This came out from, I'm loading up the PDF now to see.
That's about the same time, yeah.
Yeah. So this was, maybe there aren't some IBM people. Darn. Okay, I got IBM mixed up with MIT.
Okay.
But yeah, this was another exciting paper that came out. Reconfigurable atom arrays, where looks like a 2-qubit logic gate by scaling surface code distance from 3 to distance 7. So for context, the example that I showed in my presentation, which was here, this is a distance 7 surface code. And so in the paper, they said they're able to get a 2-qubit logic gate from this surface code. So it looks like they are kind of pushing that to the physical boundary, and they're getting into up to 280 physical qubits, whereas I know Google is only working with 100 at the moment. So yeah, I do. This paper is in the docket for me, but for me to read. So anyway, we have 8 minutes left.
Yeah.
Are there any more questions anyone would like to ask?
Oh, actually, I have a question about the previous slide. If you can go back one slide.
This one?
Yes. So here, don't you create entanglement between the qubits that you are planning to measure, and then you're measuring it? So from the very left, applying Hadamard and then C0, and then you measure your control. Well, it's a control. Doesn't it create side effects in the original qubit?
It does not.
No?
It does not, because of this extra. The main reason is because it's Hadamard gate. When we have 2 Hadamard gates, they cancel each other out. And when you have doing a Hadamard gate on a C0, that's just insane. The fact that you sort of have like these dual universes where it either switched it or it didn't, and it's equally likely that they did, because this is now in the plus state, and actually these are also plus and minus states. So I mean, again, the math, like with a lot of things with quantum mechanics, it's kind of a cop-out where you just say the math tells us that this works. If you actually you can verify algebraically that this does not change this state. If you have a state, if it's prepared this way, you run it through the circuit, it does not change. And the measurement, and again, remember, we're measuring an ancilla qubit. This qubit's job is only to serve as a measurement of 0 or 1 to say, is it likely that a Z error occurred between here and here? So And again, it's a single Z error, not two. So yeah, it's a good question, and the answer is that it just works because that's what the math says.
Okay.
It's a little hard for me to explain verbally.
No, well, it's good enough.
I wonder if I don't I think there's a concept of how much entanglement you can have between qubits, but I don't really know how to talk about that. So have you heard of that before? Like if something can be fully entangled or partially entangled, that sort of thing. I just wonder because I think what Ross is saying is we have 3 qubits here that we see, and it would seem that they are entangled. And so if we measure one of them, I think, it's like
but they're not.
What impact? Yeah. Go ahead.
So we assume that these 2 qubits are entangled. We know that because this is like essentially like a bell pair, right? It's not exactly a bell pair, but it kind of resembles one, where you have like a superposition of 2 different basis states. So there is a sense of entanglement there where they both depend on this variable, these numbers alpha and beta, and they're both prepared in like essentially the same state. But the beauty of the stabilizer code is that we're only measuring this ancilla qubit, and so we're only projecting the ancilla qubit and we don't. This is just purely for the sake of doing error correction, and these are really valid questions, because the whole point of a stabilizer is to essentially mathematically it maps the state to the +1 eigenstate of itself, which is the same as saying it just multiplies it by 1 or does nothing. But it doesn't. But what it does from an engineering standpoint is it tells us the likely, like where there was likely an error, and then where we need to go, where we need to perform a bit flip, but on the classical information, which is the output of the quantum computers. The algorithm, and I didn't even mention algorithms, because this is just like, if we want to even do Shor's algorithm, we need lots and lots and lots of these.
Yeah. Well, hey, that's that's great. I mean, it's nice to see these and get these. I haven't tried to study quantum error correction before. I've had like a tiny bit of exposure, so I think it's awesome to to see it identified here. Kind of in these abstract, simple pieces of the X and the Z and the bit flip and the phase flip, and then to see the stabilizers and the surface code, and to just, for me to have like taken a look at that Physics World article, just to hear read about someone talking about how I guess positive aspects of surface code and
absolutely, this is a very promising line of research in development.
Yeah, that's awesome. So is Fowler, is he down in Southern California, or is he in Northern?
He works at Quantum AI, I believe. So Quantum AI is in Santa Barbara.
Yeah, okay. Is Craig Gidney down in Santa Barbara also?
Yes, he's also there. They're both colleagues.
Yeah, that's nice.
Okay.
Well, that's awesome. Yeah, thank you so much. So
I think I'm gonna call time here. So we'll stop recording. Thank you all for coming.
I will make a shout out for the next time. I'm working on learning how to do some encode a protein folding problem using Qiskit. And so the next time I was thinking that, and that's related to drug discovery. There's also some new recent papers out about successes that some groups have had with these. I mean, everything's early days, so I don't quite know what level of success, but just some excitement's been generated with some methods out there for some bio science problems. So I thought I would just take that up for next time.
Great. Thank you, Natalie, for hosting. I'm going to stop recording.